Okay, can you hear me? Can you hear me? Can, okay.
Yes, doctor.
Okay, the lecture slide is clear.
Yes, doctor.
Okay, thank you. Okay, so today we will continue with 3.4. So previously we have stopped until 3.3. So today we will discuss on the mechanical forms of work. So currently we are looking at, previously we have looked at it and also the transfers, and we know that there's another type of energy transfer that is acting, which is the work, and there are various form uh, of work, and we are currently looking at mechanical form of work. The elementary mechanics work done by a constant force F on a body displays a distance s in the direction of the force is considered as a work done. So the formula for work done is W. So W stands for work done equals to Fs. So F for force and S for the distance. So meaning in a mechanical form of work, uh, force must be applied on something, and because of the force it must move a distance. Distance cover is S. If the force F is not constant, so then you can take the integral part of various part of the movement. Okay, so the sign, okay, work done on a system by an external force acting in the direction of motion is negative. So meaning what it actually is saying, so work done on a system. So meaning this is a system. So we are acting, applying force on the system. So if the external force is acting in the direction of motion, so meaning you want this box to move from here to here. So the direction of motion is to the front. Okay, so the statement say work done on a system by an external force acting in the direction of motion. So meaning the force is acting in the direction of motion. So like this. So the direction of motion from left to right, and the direction of force is left to right. So meaning you take it as a negative. So if the work done by a system against the external force, so meaning so the direction of motion is forward like this, but the force is backward, then you take it as a positive. So that's based on this, but we are not really taking this, so we will use the other conventional way. So q in, q out, w in, w out, so which is much easier to understand. Okay, so the requirement for work interaction between a system and its surrounding to exist. So there are two requirements. First, it must have a force acting on the boundary. So boundary is the dotted line. So whichever things that have imaginary boundary or the real boundary, so you can take into consideration, and the boundary must move. So if, because the formula is W equals to Fs, so if the S is 0, so S is 0, so the force automatically will not be counted. Even though the force has a value, so the work done will be 0. So the boundary must move. Okay, so if we divide the mechanical work, so the first thing that we can see is a shaft work. So shaft we always see in our car. So drive shaft and all the shaft that is acting. So similarly, the shaft, we have a term called shaft work. So meaning the work done by a shaft. Okay, for a specific constant torque. So since it will move in a circle, so if we don't call it as a force, so we call it as a torque. And the work done during revolution, so meaning how many revolution in a minute, in a second, so how many time it turns. So we take into consideration is determined force F acting on a moment arm with the radius r. generates a torque. So constant torque. So this is the formula for torque. So torque equals to F. So F in the direction tangential to the uh, circle, and R is the radius. So you are taking the you can calculate based on this formula. Okay, so the distance due a constant torque. So as equals to, so 2 pi r is uh, the distance covered by the circle. So 2 pi r, and number of n is the number of revolution. How many rounds you are taking? So let's say 3 rounds. So you need to times with 2 or 3. Okay, then the work done by a constant torque. So W shaft work done, shaft work done equals to Fs. So we know the relation between force and torque. So you can rearrange this. So bring the R down. So you can F the F. So F S is 2 pi R n. So once you cancel this R and cancel this R, so finally, so the work done by the shaft equals to 2 pi nt. Okay, so these are some of the formula that you can use. So you can see here. So this is per this for rate of so rate got dot on top. So if you are the question asks you to calculate the rate, so rate of work done by the shaft equals to 2 pi n dot t. Okay, so these are the formula for shaft work. Okay, so I already covered this. Okay, so work done by a shaft per unit time. Okay, then we have another thing called a spring. So normally we will use spring. So spring has its own mechanism. So how the work done by the spring? So work done by spring through the length of the spring changes by a differential amount dx under the influence of the force. Okay, so meaning normally the spring will be at this length. So no force applied, so it will be at the rest position. But if you apply a force, so let's say you put a weight on the spring, so the spring will elongate. So elongate. So we will calculate this dx from the rest position. So how much from the rest position it elongated. Then we will calculate. So the work done by the spring. So we can calculate based on. So this is the changes of work done in the spring equals to F dx. So force and the changes of x. So from here to this line, the rest position. So you are not taking the whole length. So that's why we are putting dx. Then we have a force apply on the spring. So force apply on the spring is F equals to kx. So what is k? So k is the spring constant. Is spring constant. I think if you see your scientific calculator, so you can find the alphabet k as a constant. So you can take that value and times with the distance covered. And the work done by the spring. Okay, so work done by spring because this is for the changes, and the actual work done by the spring we calculate by using so W spring. So work done by spring equals to half k. So k is the spring constant. So x2 square minus x1 square. So x2 is final displacement. So how much it the length elongated. So the final distance and the initial is from here. Okay, so you can calculate the work done by the system. So we can see, so a force is applied and a distance is covered. So that's why we consider this as a work done. Then we have work done on elastic solid bar work. So let's say that you have a solid bar, but it's elastic, so you can elongate it. So you also can consider as a work done. Okay, solid are often modeled as a linear spring under the action of force, contract or elongate. Okay, so we are applying normal stress. So normal stress equals to so this we covered in I think chapter one or chapter two be starting. So stress equals to force over area. So constantly apply force at one area, then it will become stress. So normal stress is 90 degrees to the plane. So you have normal stress normal equals to force over area. Then we have work done by elastic solid body. So W elastic equals to changes. So this is depends on the length cover. So initial length and the final length force dx. So we know force equals to normal stress times with area. So A bring up, so you can find the F. So you replace here in order to find the work done by the elastic solid body. Then work associated with the stretching of a liquid film. So let's say you have a film, you try to stretch it. Uh, so you stretch it by applying a force, so it will be elongated. So similar concept, but maybe it's a different understanding. So initially we have seen about spring, so almost the same. So it will elongate. So if a liquid film can elongate, so consider a liquid film such as a soap film suspended on a wire frame. So you have a wire frame. Force is used to overcome the microscopic force between molecules. So you have a molecules in between a film, and you are applying a force to overcome the microscopic force between the molecule at the liquid air interface. Okay, so if the question coming on this, then you can use this formula. So where a work associated with the stretching of a flame, so surface tension work. So we also call it as a surface tension because it is interaction between liquid and also the air. So you have a surface tension there. So we call it as a surface tension work. So W surface equals to so changes from 1 to 2. So initial to the end. So change stress surface dA. So this is from the previous slide. Okay, and you, you can have so consider this as a square. So B times so you have 2B. Okay, so the formula that you can use is 2B. So the changes is uh, the x, the changes in x. Okay, so you can cover this. So you're covering two surfaces because it's having one side and the other side. So you times with b times with 2. Okay, the force acting on the movable wire. So you have a movable wire here. So the force is 2b. So because it's having two sides and the stress of the surface. Okay, so 2b is actually the exposed surface. Exposed surface that the wire or the bar is covering. Okay, so the work done to raise or to accelerate a body. So this is another thing. So due to acceleration. Okay, so acceleration is increasing in the speed. Increasing in the speed. So when the body is accelerating, increasing in speed, so there can be work done. Okay, so if you recall, the only two form of energy interaction associated with closed system. So closed system meaning no mass in and out. So if open system, you have additional mass. So if closed system, you only have heat transfer and also work. Open system, we will have heat transfer, work, and also mass. So you can see, so this is a closed system, you have a system boundary. Mass is constant because mass is not entering or leaving. So the only energy interaction is heat moving in and out, and work done in and out. Okay, the energy transfer is not heat, not driven by the temperature difference. It must be in the form of work. Okay, so I have told this before. If the energy transaction interaction is related to temperature difference, so we call it as a heat transfer. So other than temperature different, then we call it as a work. So energy interaction based on work. Okay, so the work transfer need raise a body is equal to the changes in the potential energy of the system. Okay, so the work transfer needed to raise. So let's say you are raising one body from one point to another point. So by the height, so there will be changes in the potential energy, because potential energy, the formula is mgz. So z is the height. So there will be changes. So the work transfer needed to accelerate a body is equal to changes in kinetic energy. So meaning from one place to another place, you want to accelerate. So there's a changes in the kinetic energy. So velocity is changing. So when the velocity can double, so velocity can increase. So whatever related to kinetic energy or the velocity, so it will be related to kinetic energy, because kinetic energy, the formula is half mv square. So mass is the same, half is the same. So the only thing that is changing is the velocity square. Okay, so all these are related to the work done to raise or to accelerate a body. Then we see 3.5. So we are entering to 3.5. The first law of thermodynamics. So it's quite important because you usually will be asked in the exam. So you can pay some attention on this. So the first law of thermodynamics is relatively very easy to understand. So energy can be neither created nor destroyed during a process. It can only change form. So that is the first law of thermodynamics. So if the exam I ask, or I explain first law of thermodynamics, so you give the proper explanation with the examples, everything. Uh, then you can get more marks. So don't just answer like this, only one line. So then if the question is 5 marks, you only will get 1 mark. So another 4 marks, I cannot give you because you didn't explain further. So bear in mind. Okay, so energy, according to the first law of thermodynamics, so energy in this world, so you cannot create a new energy, or you cannot destroy an energy that already exists during a process. So it only can change form. So we have seen before this how the potential energy of the rock on the hill, on the cliff. So the potential will energy will be maximum 10. Kinetic energy will be 0. So once the rock started to fall into the ocean from the cliff, the potential energy will be converted to kinetic energy. So initially it was 10, then now maybe it already reduced to 7. So another 3 will be converted to kinetic energy. So it will be changing form. So it's not adding or reducing. So because energy cannot be created or destroyed. Also known as conservation of energy principle. Okay, so another name for First law of thermodynamics is conservation of energy principle, or principle of conservation of energy. So if the question asks to explain the principle of conservation of energy, so you must know that it's referring to first law of thermodynamics. Okay, so the change in the total energy during a diabatic process must be equal to the net work done. Okay, so a diabatic process meaning no heat transfer in a closed system. Initially, we have seen in a closed system, so you have two form of energy transfer. So the previous slide. In this closed system, so you have two form of energy transfer, heat and work. In a adiabatic process, so you have an insulation, so no heat transferring, so only work can be done. So that is what we are explaining here. So the changes in total energy of a diabetic process must be equal to net work done because no component of heat. Okay, so we see some example. So you have a potato. You have a potato. So the changes of energy, because the potato is heated up. So let's say you put it in a microwave. So you eating this up. So you are receiving heat from environment to the potato. So you, let's say in the Q in equals to 5 kilojoule. So the changes in potato now is changes of energy is 5 kilojoule. So changes means start from zero. So you are receiving plus 5. So you become 5 kilojoule. Then so let's say you are seeing a pot of water. So you have the energy changes. So we can see so energy changes inside. Normally we will start from zero, then we will see the interaction. So you can see, so Q in is 15. So let's say you are eating from the environment, you are getting 15 kilojoule, and throughout the process, you have Q out equals to 3 kilojoule. So here plus 15 minus 3. So 15 minus 3. So the changes in the energy is Q net. Why Q net? Because only Q is involved. So Q net equals to 15 plus 3 equals to 12 kilojoule. This is a diabetic. So a diabetic, we will write it down here or we will mention in the question. So a diabetic, so we know that no heat transfer happening. So the only form of energy transfer during the adiabatic process is the work done, net work done, or W net. So you can see here. Um, so from the battery, so it's entering 5. W in is 5 kilojoule. W out is not mentioned. So from the W in, so you are getting 5. So here plus 5. So you are getting 5, 5 kilojoule as the energy change. Then you have this. So work done by the shaft. So shaft. So you can see, you if you don't know whether the shaft is in or out, like here you know, so it is entering. So you see this term at the back, in or out. WSH out means so work done by the system. So this is your system. So meaning W out. So if WSH in, so meaning it is entering the system. So meaning this is plus 8 kilojoule. So that's the only one. So the changes are of the system is 8 kilojoule positive. Okay. So this is another important thing. So energy balance. So what is energy balance? So conservation of energy principles. So first law. So the net change increase or decrease in total energy of the system during a process is equals to the difference between the total energy entering and the total energy leaving the system. Okay, so you can see here the energy balance, so kilojoule. So total energy, the total energy entering. So first, whatever things that positive entering the system, so minus leaving the system. So E in minus E out equals to changes of energy. Okay, so changes. So you put the triangle. So that's the changes. So this is the energy balance equation. So E in minus E out equals to changes in E. So you can use this throughout the course. Throughout the course, this thing will be enforced. Okay, so let's say you have a system. So you can see you have W as well as Q. So you have Q in, Q out, and WSH in. So we know if whatever entering the system is in. So you have two WSH in and also Q in. So leaving the system is Q out. So only one. So how you can solve it? So this is the energy balance equation. So changes of energy of the system equals to E in minus E out. So E in you put in a bracket. Okay, E out you put in another bracket. So here Q in 15 plus W shaft in 6. Okay, 15 kilo. Okay, so the and out is Q out. So you need to minus. So you put it in the number. So 15 kilojoule plus 6 kilojoule. So make sure you see the unit. So make sure the unit are same. Sometimes the unit will be here 15 kilojoule. Here it can be 6,000 joule. So you need to convert into either joule or either both kilojoule. If not, you cannot add. So because I have seen some of your seniors done this mistake, they just take the value 15 times 6,000, 6,015. So the equation become wrong. So always check the unit. So that's why I always encourage instead of you write 15 plus 6, put 15 kilojoule plus 6 kilojoule minus 3 kilojoule. So the changes in the system total is 18 kilojoule. Okay, so I think it's quite direct. So it's just plus and minus. Okay, energy change of a system. The energy change of a system during a process involve the evaluation of the energy of the system at the beginning and the end of the process. So you are calculating at the beginning and the end of the process. So in between, so you can have a lot of processes. So we don't take into consideration all that because until you know when you want to stop, then we calculate. Because along the process, so it can add up or it can leave the system. But what will be at the end? That is what we have the concern. Same thing. So energy change state. So changes of the energy of the system. E final minus E initial. So E final is E2 minus E1. So E2 is energy at state 2 or the final state minus energy at initial state, state 1. So it must be in kilojoule. So if you recall, the total energy of the system consists of kinetic, potential, and internal energy. So this is from the part 1. So part 1 we have seen. So total energy in a system. So it has a kinetic component, potential energy component, and also internal energy. So Ke plus Pe plus U. So if you still remember lah. So if not, you refer back to the lecture note. Okay, so energy change. So if energy, you take without the triangle. So if energy change, you write with the triangle. So triangle E, the changes in E equals to changes in U plus changes in Ke plus changes in Pe. So we know this is from the part 1 also. Changes of U equals to M U2 minus U1. So if you see all these formulas, so it has U2 minus U1. So U2 is final state minus initial state. So KE of M V2 square minus V1 square. So changes in potential energy mg Z2 minus Z1. So all these formulas can be used. So if we recall, the total energy of a system consists of a kinetic. So this is the same thing. Okay, so we see some. So this is actually repeating. So if the initial and final states are specified, the values of a specific internal energy can be determined directly from the property table of or thermodynamic property relation. So this is if you are using the thermodynamic table. This was in the previous syllabus, but now since we are only studying the basic, so we already removed that part. But just for your understanding, so we have a lot of thermodynamics table. Thermodynamics table for solid, thermodynamic table for gas, thermodynamic table for liquid. So a lot of things. So even various states, gaseous state. So you have a superheated state. So all these things will be in the thermodynamic property table. We call it as a thermodynamic property table. Uh, Based on the initial and final state is specified. So let's say the question is saying, so in a superheated liquid, in a superheated liquid of nitrogen. So let's say, so nitrogen in a superheated liquid form. So you just refer to the thermodynamic table. I think table 8. I think table 7 or 8 of the thermodynamic table. So it's for superheated liquid. So you just go and check for the nitrogen. So you see what is the value for this temperature. So normally it will be given temperature at 300 degrees Celsius. So you just go and check the 300 degrees Celsius, take the value, put in your equation. So normally for your case, in your situation, we normally will give the values in the questions. So you no need to go and refer to the property table. So we already simplified some the syllabus. Okay, so if the question stating that is a stationary system, so stationary system we know that kinetic energy and potential energy equals to zero. The formula is having three component. So Ke 0, Pe 0. So the remaining is only changes of E equals to changes of U because the other two are 0. Then Y is becoming 0 because no, it's a stationary system, no changes in elevation, uh, no changes in height. So Z1 equals to Z2, so no changes in potential energy. So no stationary system is not moving, so no changes in velocity. V1 equals to V2. So the kinetic energy becomes zero. Okay. So mechanism of energy transfer, so E in and E out. So energy can be transferred in the form of heat, work, and mass flow. Uh, so generally, so this is for general. So generally, it can be in three form: heat, work, and mass flow. But for closed system, no mass flow. So only heat and work. So heat transfer Q. So what is Q? So heat transfer to a system, heat gain, increase the energy of the molecule and thus internal energy of the system. So heat transfer from the system, heat loss decreases it. So what actually happen when heat transfer? So heat transfer. So you are getting the heat transfer from the environment to the system. So when the heat is added to the system, so molecule in the system, it will receive more energy, so it will move more vigorously. So what will happen as a result? So the internal energy of the system will increase. So that is what this statement is saying. So when the energy from the system is going out, so we consider as a heat loss by the system. So the molecule in the system, it will move less vigorously because energy is lost. Similar like this. So if we eat, we will get a lot of energy. But if we eat and we also doing a lot of work, so we will have it the energy will be moving out of the system. Then we will become weak. So similar for heat transfer. So work also the same. Yeah, work transfer to a system, work done on a system increase the. Yeah. So if the system work is done on the system, okay, so work done on the system increase the energy. So when someone is helping you to do work, so you save your energy, right? So you will have a lot of energy. So if you need to do a work, then your energy is going out. So what will happen? So the energy of the system will decrease. So mass flow also the same. So mass enter a system increases the energy of the system. So mass, so food is entering your body, so your energy will increase. So when you are sweating or a lot of toxic leaving from your body, uh, so you are leaving. So the energy of the system will decrease. Okay, so this actually a lot of repetitions just for to emphasize. Okay, so E in minus E out equals to changes in the system. Okay, so you can see. So you have a closed system. So closed system, sorry, control volume is an open system. So open system, you will have mass in and mass out. Okay, and also you have a work in and work out, and you have a Q in and Q out. So control volume. So if you rearrange this, you expand this formula, so you can put it like this. Okay, E in minus E out equals, so this Q uh, component, Q in minus Q out plus W in minus W out plus E mass in minus E mass out. Okay, let's hold on. Okay, sorry, disturbance. Okay, so continue. Okay, so you can put it like this. So you will have six quantities on the right hand side of the equation. So you have a Q in 1, 2, 3, 4, 5, 6. So based on whatever things I explain in the system, you can just replace. So if it's not mentioned, so you just can leave it out. Let's say the question is only giving Q in, so Q out is not mentioned, so you can just cancel it out. So you just replace it, then you can find the energy change in the system. Okay, so if a diabetic system, so both will be 0, Qn and Q out will be 0. So no work interaction, so work in and work out become 0. And closed system, no mass in and out, so E mass in and E mass out becomes 0. So generally, you only need to remember this formula for this thing, this chapter. So using this formula, you based on the information given in the system, so you will know which one to make it 0, which one not to replace with value. Then you can calculate the changes in the system. Okay, so again the same formula. Okay, so energy balance E in minus E out equals to changes in the system. So energy balance in rate form. Okay, so rate form, so I have told, is based on time. Okay, so it's related to time, and rate form, you always will have a dot on top. Okay, E in dot minus E out dot equals to changes in the system uh, over time. Okay, over time. So per dt. Okay, so for constant rate, so the total quantities during the time interval. This is another formula that we have discussed in part 2. So Q equals to Q dot times with time, changes in time. So W equals to W dot. Okay, so W dot times with changes in time. So changes in energy equals to changes in energy over time times with dt, delta t. Okay, so if the question is mentioning smaller e, so e in minus e out equals to changes in the system. So this is for per unit mass. Uh, is either the question is giving smaller e in the question itself, or the question is mentioning per unit mass, or it will give the values in kilojoule per kg. So all these are indication that the question is related to per unit mass. Okay, so E in minus E out small equals to changes in energy system per unit mass. And then you can have in a differential form. Okay, so differential is like a small differences. So it's the same, practically the same. So changes in energy in minus changes in energy out equals to changes in energy of the system, and this is per unit mass. Okay, for a closed system undergoing a cycle. So a cycle we have discussed before. Cycle meaning, so you start from point one, so you go one round and end at point one. Okay, so that is one cycle. So complete. So let's say you have few point from point one to point two to point three to point four, then go back to point one. So if starting and uh, end state are the same, so we know that the system is undergoing a cycle. So when the cycle is involved, so you know that E2 equals to E1. So this is the equation of the system. So E2 minus E1 equals to 0. So if you rearrange, so minus E1, so you bring to the other side, so you can get E in equals to E out. So that's why Q net equals to W net. So that is if the question is mentioning is related to a cycle. Okay, so for a closed system, if closed system, okay, so W net out equals to W net in. So net out equals to net in. So this is if it's for a closed system. So this is for a closed system undergoing a cycle. So this is generally for a closed system. Q net out equals to Q net in. This is on the rate form. So you have a dot on top. Okay, so 3.6. Okay, energy conversion efficiencies. So you want to see how efficient the energy conversion, because you want to change from one form to another form. So when you are changing in between, you can have energy losses. Maybe because of long wire. So compared to using a short wire and long wire, so if you use long wire, so the energy can lose more. So that's why you try to make it lesser. So imagine in a real life example, so you are taking your car, so you are driving. So let's say from Ulu Power Putra campus, you want to go to Arau town. So let's say you are taking a long road. So your car will consume more petrol. But if you are taking a shorter route, let's say you are taking a direct highway, then you will reach faster. At the same time, the car will use lesser petrol. So, meaning shorter road will always will be more efficient than a longer winding road. So that is how we know. So efficiency is like that. Okay, so how well an energy conversion or transfer process is accomplished. So let's say you want to transfer from one point, okay, potential energy, you want to change it to kinetic energy. So potential energy you have 10. So you want to get 10 kinetic energy. You want to convert it 10 to 10. But because due to process 10, once you convert, you only get a 9. So you lost one or 1 kilojoule. That meaning, so the efficiency of the system is 90%. The conversion is 90%. So 10% it lost. So it's like that. So efficiency you can calculate based on, so efficiency the symbol is like N. So like you can see like N. So if you see this symbol N, so it's actually referring to efficiency. So efficiency equals to desired output divided by required input. So you also can put it as E out over E in, energy out over energy in, or yeah, 1 minus E loss over E in. Okay, so normally we will use this formula because we want to check how much energy loss. Okay, or it depends on the information given in the question. So if the question give E out and E in, then you can calculate directly. So if the question give E loss and E in, so you can use this side. So various devices having various formulas. So let's say the question is mentioning a pump. Then you can use these two formulas. So changes in electrical or mechanical fluid over W shafting equals to W pump uh, of the system divided by W pump uh, in the environment. Okay, so in the question. Okay, so we will see one question regarding this later. Okay, so and turbine. So let's say there is a involving a turbine. So W shaft out. So this is all red, because got dot over the modulus of changes of energy mechanical of the fluid, or you can use W turbine over W turbine. So of the E and the energy, and we also can have other things, so like motor, generator. So we have pump to motor. So you have two. So you have times with both. So you need to calculate separately, and you need to change. And you have a pump motor. So you have this formula turbine generator. So you can calculate two, and you need to combine, or you can use directly this formula. And the turbine generator you can also calculate based on this. So in your exam, if let's say all these things you need to calculate, so the efficiency, let's say pump motor. So the normally the formulas will be given in the appendix. Okay, so as a summary for chapter 3, so we have studied the form of energy. So we have studied the macroscopic, uh, so involving kinetic and potential, and we also study about microscopic form of energy, so internal energy. So we have studied about sensible, latent, chemical, and nuclear energy. So we have studied about energy transfer by heat. energy transfer by work. Uh, so these two we have covered in part two. And then we have studied about mechanical form of energy and first law of thermodynamics and energy conversion efficiencies. All this we have studied today. Okay. So any questions so far? So any questions? Anything you want to clarify?
No, doctor.
Okay. So I hope you all understand. So I will give these recordings. I will record in two part. So first part will be the class earlier. So then I will stop the recording. Then I will go to the second one. So there will be two attendants. So second part we will look on the some of the question. We have six questions. We will see. We will see the six questions in the second part. So I'll give like 15 minutes rest. Then we will come at now is 10:53. So wait for a while. I will take the attendance for part one. So I will pass the attendance link first, so that you can fill. Okay, stop the recording first.